the next section we look at a much more intense form of radical division where the bottom does not come out cleanly and requires you to take an extra step called rationalizing the denominator. Let's do an example first and let's talk about why you would ever do such a thing. So we see we have a 2 over a 2 square root 3n to the third. First thing we can do is try to break down that root. We only have a root on the bottom, so no fraction here. We just need to break it down. And 3 doesn't break down, so that's just going to be a leftover. N breaks down into n times n times n. Pair of n's and a leftover there. So on the top we have a 2. On the bottom we have a 2 times an n that comes out. We have in the square root, the leftover is 3 and an n. Now if I'm continuing to reduce this, I see that I have a 2 and a 2, top and bottom. So 2 divided by 2 is 1, 2 divided by 2 is 1. And that's about all I can reduce from top to bottom. So it would seem that my answer ought to be 1 over, and then 1n is just n, square root 3n. This would seem like a done answer to most reasonable people. However, because of the fact that there's a square root in the denominator, you have to take an extra step. There's nothing you can do to simplify that. Instead, what you need to do is multiply the top and bottom of the fraction by exactly that root, that fully otherwise simplified root, square root of 3n on top and bottom, to get your final answer, which is the square root of 3n over n times, and now here we have square root times the square root, which is the equivalent of saying square root of 3 times, and I'm going to move them around in order, 3 times n times n. That's all being multiplied. Pair of 3's comes out as a 3, pair of n comes out as an n, and so on the bottom I have a 3 and n squared. So my final answer is the square root of 3n over 3n squared. Weird. What we're doing here when we rationalize is getting it in a common form so that since there are many ways to leave this expression, they decided long ago on some standard way that everyone would do it so that if you had something, you would get it into the same form as everyone else who was solving the problem. And the rule they decided on was no roots in the denominator. There's historical reasons for that, such as the way that slide rules would work, not being able to divide by roots and stuff like that. Basically things that are not relevant to any of you. But they had to pick some standard, and so they chose this. So we get to go through the fun of learning this system. So let's try another example. Here we have roots on top and bottom. So since we have that, let's take advantage of turning this into a single square root fraction. So we have a 2 and a 4 out front, 4 on top, 2 on bottom, times, and I'm going to break it up this way, 12n to the 4th over 20n to the 4th, all under a giant square root. With that giant square root, we can reduce anything inside of it. So n to the 4th and n to the 4th are the things that stick out to me. Let's get rid of those. Let's reduce them since they will go away when you divide out all those n to the 4th, divide out to 1 on top and bottom. We also have a 12 and a 20. Now 12 divided by 4 is going to be 3. 20 divided by 4 is going to be 5. So we have a square root of 3 and a square root of 5. And I'm actually going to just rewrite this right now. Square root of 3 over square root of 5. And then cross that all out. Because otherwise those numbers are so messy that I'm going to lose them. Continuing on, I have a 4 and a 2 out front. And since that's a fraction, all multiplication, divide the top by 2, divide the bottom by 2. And I put 2 over 1 out front. So my cleaned up answer appears to be 2 root 3 on top. And then on bottom, 1 in square root of 5, so just square root of 5. Like we said earlier, that would seem like the done state, but anytime we have square roots in that denominator, we have to do something about it. We have to multiply top and bottom by the same thing, that square root. So on top, 2 times square root of 3 square root of 5 is going to be 2 square root of 3 times 5 is 15. 3 and 5 don't break down, so that's why we just go straight to that. Root 5 times root 5, root 5 squared, just 5 comes out, and that's always going to happen that way. And since 2 and 5 don't reduce, square root of 15 doesn't break down, our final answer is 2 root 15 over 5. Let's go ahead and do another example here. Number 19. The place we want to start with this one is probably going to be the fraction again. So in this particular example, it may end up working against us, but whenever I see common pieces, I like to break it down that way. So out front, there's an invisible 1. I'm going to write that just to make it clear. And then there's a square root of 2x over 3x squared. The x and the x will reduce down, so I can get rid of that and make that x to the 1, since there is one more x on the bottom than the top, x to the second on the bottom, x to the 1 on top. I'm left with x to the 1 on bottom. 2 and 3 do not reduce in any way, so not much out of that. What I end up with for my answer now is essentially square root of 2 just on top. The 1 you can choose not to write that. The bottom I have 5 square root of 3x. So really not much has changed. Final step then is to multiply top and bottom by whatever is under the root in the denominator. So not the 5, just the root 3x. And when you do that, you end up with, on bottom, 5 times 3 times 3 is 3, or 3 times 3 is 9, but then square rooted is 3. X times x is x squared, but then square rooted is x. So you write all that on bottom. On top, you have a square root times a square root. Remember what we said, it becomes 1 root. So it's really just 2 times 3x, or square root of 6x. So our final answer, cleaning this up, square root of 6x on top, 5 times 3 is 15x on bottom. Some of these other examples will offer some good practice. Try some of these on your own. There are many strategies for these. Some of them are more time consuming than others, but make sure that you always leave your final answer with no square roots left in your denominator.